So in this tutorial we're looking at the reactions of alkene systems with a range of electrophiles. So we remind ourselves that an alkene is an sp2 carbon, so the two sp2 carbons adjacent to each other with p orbital overlap, so an unhybrid p orbital, non-hybrid p orbital on each carbon atom overlapping to form the alkene double bond system. So the first reaction looks at the reaction of this isoprene unit with HCl, and we need to judge this reaction in terms of the orientation, the regioisomers of reaction. So we take this as a mechanistic guide of a reaction with an alkene system as follows, and an alkene of course is a p orbital overlap, so it's a p orbital character which is to react with the HCl, so the hydrogen chloride as a permanent dipole in bond, delta positive hydrogen, delta negative chlorine. So the p electron density is nucleophilic towards the electrophilic hydrogen here, both electrons move towards the hydrogen, and you're then left with the formation of a carbocation. So with two potential carbocations here, so if it was now to include the hydrogens in this system, with two potential carbocations that could form, do we put the positive charge on this carbon or this carbon? So if we were to form the reaction where the hydrogen attached itself to this carbon, we then would transmit this as a carbocation, where the p orbital here on hybrid p orbital is now the carbocation centre. So we have here an sp2 carbon, we have an sp3 carbon formed. So we remind ourselves we move from sp2 to a new configured sp3 centre. We have a tertiary carbocation, or the hydrogen can attach itself to this carbon in the electrophilic reaction, so we then would form this as a carbocation centre. So we have sp3 to sp2, and then we would then have this as a secondary carbocation. So this is more stable, the tertiary carbocation is more stable, so the reaction of the chloride now would invoke itself onto this carbon, so the nucleophilic chloride would donate electron density to the p orbital of this carbon, so we would then be resulting in product as shown. So we would end up with this 2-chloro 2-methyl propane product. This is the major isomer, and as a minor isomer formed, any chloride here as a nucleophile would attack this carbocation, so we would end up with this product as the final product at this point. So this will be 1-chloro 2-methyl propane. So the reaction or the second molecule in that scheme is as follows. Adjust my paper if I can. So what is the second reaction that we've got here? We've got an aromatic system, which is then bridged into the alkene system here, and the alkyl chain, the ethyl chain as shown. And again, this is reaction with HCl, so delta positive chlorine, hydrogen delta negative chlorine. So the p electron character, the double bond character of the bond breaks towards the hydrogen, and then we break the hydrogen to chlorine bond as formed. So again, if we were just to include the p orbitals as shown here as the alkene bond moving out towards a hydrogen, we would form again a mixture of two isomers, two carbocations in this intermediate state. So our intermediates here, what would they be? So let's just draw the backbone out of the molecule. So that's our backbone of the molecule. We can either donate the electron density where we form this. Here is the p orbital with carrying the carbocation charge, or we could donate to this as the carbocation centre. So what do we have? Well, essentially we have in both scenarios here secondary carbocations. So we have secondary carbocations in both scenarios, but this carbocation is stabilised through resonance forms. So stabilised by resonance, and I'll show you this in a moment. But this is not stabilised by resonance at all. So the incoming chloride again would react at this point and form our new product as shown. So this is the major form product. So again, if we had any chloride nucleophile attack in here, our minor form of product would be this system. So why is this stabilised by resonance? And what is resonance? So we look at this in another way now and say, well, let's draw out again the benzyl system, and let's show the carbocation here at this position. So I've just said benzyl system. So this here is a benzyl functional group which we've got, but the positive charge is on the carbon next to the aromatic ring, so it's benzylic as a carbocation. This is a benzyl carbocation. And why is this stabilised by resonance? What have we got as resonance? Well, we can just draw one resonance tautomer in this fashion to say we can move the electron character out of the aromatic ring towards this as our first resonance tautomer, and then this here can be stabilised further. Just the next resonance tautomer, and then we have again a further resonance point that we could draw in. So why do we have resonance? Well, if we were just to look at this as a aromatic cycle where we can draw the hexagon ring system as shown, let's now draw the p orbitals in a plane, and I'll just put some dashes in to say where we believe the double bonds could sit in this form. But the carbocation is a positive carbon here. So the benzylic carbocation as we've got here can be drawn in this sense. So the p orbital can overlap with the aromatic p orbitals, and electrons can literally flow out between these carbon-carbon bonds in the aromatic ring towards this p orbital, towards the sp2 carbon in the aromatic ring, this sp2 here, and form the first resonance tautomer that we have here. So because we have vacant p orbital, the vacant p orbital with the carbocation charge being benzylic, we have resonance of the electron density over the ring, and this is stabilised. So we have stabilisation by resonance, and this gives us here our major product, and this is our minor product. So we'll put this in here as stability by resonance. The next part to this is, as a sequence, is this C as such. So what have we got here? Well, we have now again this other alkene system that we can draw as shown, and this reacts with HCl. So again, what do we have? Well, we have mechanistically the electron density moving out of the double bond towards the hydrogen, and we have the HCl bond breaking in this manner. Again, delta positive hydrogen, delta negative chlorine, due to differences in electronegativity, permanent electronegativity difference, and we will form again a potentially mix of two carbocations. So what do we have as the carbocation? So if we draw the skeletal form of the molecule out, we can either put the positive charge towards this carbon, or we can put it towards this carbon. So we have here, we have a secondary carbocation, or we have a primary carbocation. and by energetics this is stable, more stable. This is lower activation energy to form this carbocation centre. This is more stable. So nucleophilic chloride has the chance to move in nucleophilically towards this carbon here. We form this as the major product. So this is the major isomer formed, and this primary carbocation can attack so it can be attacked by the chloride as follows to give that as your product. So to answer question 1, what do we form as products? We form the major isomer as shown, the major isomer as shown, and the major isomer again. And just to give you a quick overlap of this, is the reaction of alkenes with electrophiles. We must break the p orbital character of the double bond, and we then, when we form these as intermediates, so I should really just go over and say these are the intermediates formed. I'll go through and put all my intermediates in. We form intermediates with reconfigured carbons. So we go sp2, we retain sp2 character to move to sp3. Again, retain sp2, move to sp3. And in this scenario, sp2 is retained, sp3 is reconfigured, sp3 is a reconfiguration, sp2. So when you form your intermediate from the alkene system, you also are rehybridized in one of the carbon atoms immediately, and the following carbon atom is rehybridized by the reaction of the nucleophile, in this case the chloride.